we moved past application exercise 2.5 without getting to it in class. It's not super hard, and these, what we might call computational problems, tend to be done by the most technically able student helping everybody else do them, and it's not necessarily the way to harness the group energy best. Still, I want you individually to be able to do this kind of problem, so I'm going to show you how it's done. Here we have this problem. Suppose that there are currently 6,800 tons of sulfur dioxide emitted in Smogville. Policymakers want to reduce sulfur dioxide emissions by half, so they're going to be cleaning up 3,400 tons. That's going to be important. And then we have these marginal costs associated with each of three possible cleanup methods. And our intuition would tell us, oh, just use all of method 1 because, 0.01 is less than 0.02, 0.05, and that would be wrong. And the reason it would be wrong is that while if we're producing the same quantity across each method, method 1 will be cheaper, because marginal cost rises with method 1 application. At some point, it's going to perhaps make sense to use method 2 and or method 3. So how do we do this kind of problem? Let's just dive in. So the first thing you do is to realize that we want to clean up 3,400 tons. So across all three methods, the amount cleaned up is going to have to add up to 3,400. That's a critical insight. Can't do the problem without it, in fact. Okay, what's next? Well, what's next is this application of what we call the equimarginal principle. This might be the first time we've seen it in this course, Econ 333, week 3, I think. Anyway, it's the equimarginal principle in this case tells us that at the lowest cost cleanup option, the marginal cost of method 1 should equal the marginal cost of method 2, should equal the marginal cost of method 3. I should say if Q1 is greater than 0, Q2 greater than 0, Q3 greater than 0. The way you know that you shouldn't use one of the methods is if you do the problem the way I'm going to show you and you get a negative quantity. That just tells you, oops, we're not going to want to use that at all. Negative quantity doesn't make any sense. So if you get something like that, it's either you made a math mistake or you just wouldn't want to use that method. All right, so the intuition behind the equimarginal principle is, why should the equimarginal principle hold? It's easiest to explain by talking about why you wouldn't be minimizing costs if the equimarginal principle didn't hold. Let's say the marginal cost in plant 1 was lower than the marginal cost of, I should say, methodology 2. So if that's true, I can clean up one less unit with methodology 2 and one more unit with methodology 1, and I'll have the same amount of cleanup, but I will have lowered cost because I shifted from a relatively high cost unit cleaned up to a relatively low cost unit cleaned up. So if ever the equimarginal principle doesn't hold and the cleanup in each methodology is greater than 0, then you can always reduce costs by switching from a relatively high cost unit cleaned up. Remember, marginal cost is simply the cost of the last unit cleaned up, to a relatively low cost, and you would reduce costs without reducing cleanup. So only when those three marginal costs are equal, if we're cleaning up across all three methods, only when those three marginal costs are equal would we be minimizing costs. Well, this gives us a way to solve this problem. I'll go back to the problem to remind you. Notice that the marginal cost of methodology 1 is 1/100th, 0.01 times however many tons we clean up with method 1. Marginal cost of method 2 is 2/100th or 1/50th times whatever quantity we clean up with method 2, and marginal cost of the third method is 1/20th times 0.05 times however much the quantity we clean up using method 3. So those expressions for marginal costs let us solve this problem. Let me show you how. So let's call this equation 1, let's call this equation 2, and then from this equimarginal principle we can derive equation 3, and that simply says that 0.02 Q2 has to equal 0.01 Q1 if we're minimizing costs, and we can simplify that to get that Q2 has to equal 0.5 Q1. That's 0.5. So that's going to be our one of the relationships we're going to need to solve this. And then another one is going to be, we also know that 0.05 Q3 is equal to 0.01 Q1 if we're minimizing costs. And we can simplify that to get Q3 is going to equal 1/5 of Q1, which is 0.2 Q1. All right, so we'll call that expression 4. And now we can plug 3 and 4 into 1, and we'll be able to solve for Q1, and then we'll be able to go back with a value for Q1. We'll be able to go back to 3 and back to 4 and solve for Q2 and Q3. So here we go. Subbing 3 and 4 into 1 gets us Q1 is whatever Q1 is, plus, remember Q2 is equal to 0.5, or 0.5 times Q1, and then that's a 1, and then Q3 is going to be 0.2 times Q1, so I can just sub in 0.2 times Q1, and all that has to add up to 3,400. So I combine terms, I get 1.7 Q1 equals 3,400. That means Q1 is equal to 3,400 divided by 1.7, which is equal to 2,000. Yes, I cook these numbers to be nice and round. And remember that Q2 was half of whatever Q1 was going to be. So Q2 is 1,000, and Q3, excuse me, I've got something in my throat. Q3 is, excuse me, 1/5 of Q1, which works out to be 400. And notice that 2,000 plus 1,000 plus 400 gets us all 3,400 tons cleaned up. If ever you don't get the desired cleanup level by adding those up, you know you made a math error. If ever any one of these terms is negative, you also know that, well, you either made a math error, or it could be that if you get Q2 should be negative 200, well, no, Q2 can't be any less than 0. It must be 0, and then recalculate with just the two viable methodologies in play. But anyway, in this case, all three methods were used, and the quantities cleaned up with each method are 2,000, 1,000, and 400 respectively across Q1, Q2, Q3.